My name is Nicholas Karabin. I'm a chemical and biomedical double major here at Carnegie Mellon and CIT. And the project I've been working on is microstructured coatings for controlling the host response to implants. So basically the primary issue is when you have an implant, there's going to be some type of immune response from the host. It's particularly whenever you implant something that's hydrophobic. If you're implanting this hydrophobic material that hates water, and you're in an aqueous environment due to the human body. Now, when this occurs, it's natural for the proteins that kind of flow around this implant to absorb onto the surface to kind of put a protecting barrier to protect the hydrophobic area, the water-bearing area from this aqueous environment. When this occurs, the proteins eventually denature. The denaturation of the proteins causes a immune response that can range from chronic inflammation to device failure. So in order to prevent this, individuals are looking for a way to control the host response to that implant. And one method in doing so is to use a hydrophilic coating on top of that implant that prevents protein absorption. One current issue with this is that many of these polymers that they would use for this are synthetic polymers, and they don't always respond biocompatibly. So in this project, we are co-grafting polydiethylene glycol methyl ether methacrylate to HA. It's kind of a mouthful. And in doing so, we impart some of the characteristics of that polymer to the HA. Polymer is an interesting polymer because, number one, it's extremely adhesive, so it's great for making something that's not going to stick to an implant like HA, stick to it. Number two, it's temperature responsive. So as a kind of term known as the LCST, the lower critical solution temperature, and the LCST is the temperature that represents when this polymer in solution is going to act in a single phase or in a binary phase. For polymer, the LCST is 26 degrees Celsius. So this allows for the application in which the polymer solution, the polymer solution, or the HA polymer solution can actually be injected into the patient kind of non-invasively and as a liquid. And then once the human body increases the temperature of the polymer to 37 degrees Celsius, that polymer is going to crash out of solution because its LCST is 26. That's going to allow it to kind of coat that implant rather evenly, non-invasively. This area is simply the synthesis behind the polymer. We use ATRP, which is atom transfer radical polymerization. It's a controlled method in which we first synthesize the polymer, then we substitute this bromine group with ethylene diamine, allowing us to have a free amine group. With this free amine group, we can then bind the polymer to the HA by reacting the amine group with the carboxylic acid group that's in every repeat unit in the HA. And that allows us to develop this HA polymer construct. This is the loading phase in which we loaded our polymer construct onto the sensor tip. We wash it to make sure any unbound polymer is not going to influence the testing. We wash it one more time to get a baseline, which is this third segment right here. As you can see, there's a layer of polymer on the sensor tip. Next, we tested our polymer with two different proteins, bovine serum albumin and fibrinogen. As you can see, there's actually a decrease in the thickness layer involved on the end of that center tip, which implies that there is no protein absorption. Basically, these are the results that we'd hope to achieve. And the next phase of this experiment, or this project, would be to functionalize the backbone of HA, not only with the polymer, but also with anti-inflammatories. Therefore, we could localize these anti-inflammatories at the implant site. The early indications are pretty promising right now as actually using this as a coating material, because number one, HA is just a material that we like to use because it's natural. We know how it's going to react to the body. So anytime we can incorporate that, with knowing that, we just kind of want to see what kind of variations we'll have on those effects. We haven't done any in vivo testing, and our in vivo testing is really kind of in the early stages right now, in which we're just trying to see whether or not the synthesis process, or the synthesis, has maybe stopped the antibody from being able to react. That's hence the Forte Bio experiment. Oh, actually, sorry, we haven't even got to that step yet. We're still only on testing whether or not the protein's going to absorb. But I would say that testing right now is still in its early infancy, but it looks rather promising at this stage.